The trig identity that I'm writing here will be useful in solving this problem. If we multiply the identity by A, then we can see that this quantity, 2A, represents the amplitude of the standing wave. AS, the standing wave amplitude, is twice A. The quantity in front of the spatial variable x is the wave number k, that's 2 pi over lambda, and the quantity in front of the time t is the angular frequency omega, that's 2 pi f. So in part A, the amplitude of each traveling wave is half the standing wave amplitude. That works out to 2.22 millimeters. In part B, the wavelength is 2 pi over the wave number k. The wave number k is 32.5 radians per meter, so the wavelength equals 0.193 meters. In part C, the frequency f is omega over 2 pi. The angular frequency omega is 754 radians per second, giving a frequency f of 120 hertz. In part D, the wave speed v is omega over k. Substituting the values for omega and k gives us a wave speed of 23.2 meters per second. And finally, in part E, we're asked to find the wave function for the two traveling waves that make up the standing wave. We can start by writing down the amplitude A, 2.22 millimeters for each standing wave, and then comparing the left-hand side of the identity at the very top with the expression they gave us in the problem statement, we can see that B corresponds to kx and C corresponds to omega t. Substituting these into the identity, left and right-hand side, gives us this expression. On the left is a standing wave, and on the right are two traveling waves. This traveling wave I'll call y1. It's traveling in the positive x direction. And this traveling wave I'll call y2 is traveling in the negative x direction. They each have the same amplitude, wave number, and angular frequency, but they're traveling in opposite directions.